Hello and welcome to Apia in Western Samoa. We're here to tell you about an event involving NZ60 and Air New Zealand 767 on the night of the 29th of July 2000. On board was a captain, 2 first officers, 8 cabin crew and 165 passengers. What we have subsequently learnt from this event provides a free lesson for us all. This event will interest even the most experienced pilots, as it has revealed some very important lessons. Lessons about the way in which an ILS system functions, and lessons about the need for good crew cooperation. As professional pilots, we spend a lot of time doing cross-checks. These are based on our knowledge of how aircraft works combined with our understanding of human error. Cross-checking of the aircraft and ourselves is designed to trap errors and prevent them creating a problem for either ourselves or our passengers. I guess it is fair to say that the only 2 things we have really learnt to trust are the windsock and the ILS.
The level of trust that pilots and aircraft designers have in the ILS system is shown by the fact that in low visibility we routinely fly down to 200 feet and in some cases conduct auto-land approaches right to touchdown. We believe that as long as the autopilot is coupled to the aircraft, we have no warning flags and there is a valid ident signal from the approach aid, we can conduct a safe auto-land approach. But it is not that simple. To help us understand, let's go back to the night of the 29th of July in 2000. Around midnight, flight NZ60 was en route from Auckland to Apia. The captain was flying the aircraft. During their pre-flight briefing, they discussed all the NOTAMs regarding the degraded state of the aids at Apia. The Faliolo VOR, the ILS DME and glide path for runway 08 were all unmonitored. Only the Faliolo DME and NDB were clear of defects. As a result, they were cautious and made a thorough preparation and briefing. Their planned approach was going to take them around the DME arc to join finals for runway 08. It was a dark, moonless night and the controller at Apia was reporting scattered cloud over the airfield. As an extra precaution, they briefed for the VOR DME approach to runway 08 in case the ILS was not functioning. In a moment, we'll let the crew help tell you the story as they made their approach for runway 08.
The glide slope capture happened almost immediately after the approach mode was selected. The captain had the aircraft in vertical speed mode to slow down and was concerned that the aircraft seemed to accelerate as it pitched down with the glide slope capture.
As we came around the arc, everything was fine. But suddenly, at glide slope intercept, everything became rushed. The aircraft pitched down, but now the aircraft was a lot faster than you should be as you commenced the descent for the ILS.
But the ILS indications were all correct, so the captain concentrated on managing the energy problem.
I reconciled it by saying tailwind, heavy weight.
There were no flags, no warnings of any sort to indicate that there was anything other than an autopilot capture of a valid localizer and a valid glide slope.
The first officer did not remember talking to Apia Tower about this time because he was focused on assisting the captain with the management of the aircraft energy problem.
If we were getting preoccupied with managing the aeroplane and slowing down and configuring.
At 1,000 feet, the crew had completed the landing checklist. Each started to think again about the unease they had felt when the aircraft had captured the glide slope so quickly.
Why were we rushing? Why was the aeroplane going down so quick? Why were we needing to use speed brake? Why were we needing to use the gear?
I was heads down managing the aircraft all the way through till the landing checklist was complete.
With the aircraft now set up for landing, they started to revisit their doubts. They were looking for something to confirm that the on-slope glide slope indications were, in fact, correct.
Looked up to clarify in my own mind where we were. Something in my mind said things were not right.
All 3 pilots looked up through the forward windscreens, expecting to now see the runway lights in front of them. The captain reported seeing a mishmash of lights and thought that scattered cloud, previously reported by Apia Tower, might be partially obscuring them. The other pilots could not see the runway lights either.
Well, when I looked out the windscreen and I couldn't see the airfield and I expected to.
I remember looking up the windscreen and all I could remember seeing is 2 dim red lights. I thought, oh, that's interesting. where's the airport? It didn't make any sense to me, so I came back inside and saw that the glide slope and the localizer are both still centred. There are no warning flags, and the 3 autopilots are still engaged.
The first officer looked out of his side window and was surprised to see that the lights from the village on the adjacent island were so close. He voiced his surprise.
Well, shit, those lights are close.
At the same time, the captain was doing a DME cross-check, but was unable to make the answer tie up with the aircraft altitude. He decided that there was something seriously wrong with the ILS instrumentation. The third pilot also checked the DME against the altitude.
I did the first DME check, it didn't make sense. What had I done wrong? And suddenly it all clicked that my DME checks were saying we weren't where we were supposed to be, and almost instantaneously all 3 of us said, go around, go around.
Go around, go around.
The autopilots were disconnected and a missed approach was conducted to a safe altitude using only the standby instruments. The captain chose to fly to a safe position to assess what should be done next. He had a feeling the aircraft had deceived him and he needed to re-establish his trust in the instrumentation before returning for another approach.
Once we'd levelled off at 4,000 feet, I was very keen for the captain to put the autopilot in, and I prompted him, but I was keen to for him to offload himself, and in doing so offload all of us a bit so we could ascertain exactly what we were going to do and use the autopilot to help join the arc and fly a second approach.
The first officer called Apia Tower on the radio.
We've had a false glide slope capture.
Restoring their confidence in the aircraft systems was not easy, and all 3 pilots discussed their situation carefully. Their discussion led them to suspect that the glide slope for runway 08 was giving false information and could not be trusted. They then planned and executed a second approach, using the localizer and ignoring the on-glide path indication. The subsequent investigation revealed some important lessons in 2 main areas. The first lesson is the technical understanding of what errors can be present in the ILS. The second lesson is in how good crew performance can trap those errors and prevent an accident.
Let's look first at the technical aspects of the investigation, and specifically the ILS ground system. A basic ILS system provides horizontal and vertical guidance information to an aircraft. An ILS has 5 distinct components. These are the localizer transmission system, the glide slope transmission system, co-sighted distance information from a DME or a marker system, a second standby transmitter, and a remote control and indicator system. The Morse code identifier signal, or ident, is carried on the localizer carrier signal only. The ramifications of this are not widely appreciated. An audible and valid ident is, therefore, only guaranteeing you that the localizer carrier signal is transmitting. It does not ensure that the glide slope is transmitting. If some components of the whole ILS system are not functioning, it is recommended that they should be switched off. 2 separate transmitters generate the localizer and glide slope signals. Each transmitter receives signals from a pair of amplifiers. Historically, we've been led to understand that both the electronic localizer and glide slope signals form narrow, tightly focused beams which the aircraft receiver sensed. The actual signal pattern is, as you will see, rather different. The 2 glide slope amplifiers provide signals to the glide slope transmitter. The transmitter then routes the signals to 2 independent aerials. The 2 aerials that create the total glide path signal are located on a tower near the runway and abeam the touchdown point. The lower aerial radiates the carrier wave. This carrier is formed by a UHF signal and is modulated or adjusted with 2 other frequencies of 90 Hz and 150 Hz. The resulting signal contains equal amplitude 90 and 150 Hz modulations. This carrier wave on its own does not provide any glide path guidance. The upper aerial radiates 90 Hz and 150 Hz modulations only. These signals are transmitted in a specific phase relationship, with the 90 Hz and 150 Hz signals being transmitted by the lower aerial. As a result, a complex interference pattern is formed, effectively creating upper and lower side lobes as shown in the diagram. The null between the 90 and 150 Hz side lobes define the glide slope. These patterns are designed so that if the aircraft is below the desired 3-degree glide path, it will sense a predominance of 150 Hz. If it is on the desired glide slope, it will sense the null between the 90 and 150 Hz signals, so that the flight instruments will show on slope. If it is above the desired 3-degree glide path, it will sense a predominance of 90 Hz. This is the normal operation of the glide slope transmitter. Let's look at the abnormal ILS glide slope transmission that occurred on the night. The glide slope side lobe amplifier was not operating, so the aircraft only received the glide slope carrier wave. Because the carrier signal has equal amplitude 90 and 150 Hz modulations, this signal was electronically interpreted as being on glide slope. But the ILS system is supposed to protect against this type of malfunction. So what are the measures that should prevent a faulty glide slope transmission? The glide slope system has a normal or primary transmitter and a backup transmitter. A sensor on the radiation field monitors the signal integrity. And there is also a status indicator and alarm in the tower. For a Category 1 ILS, ICAO rules specify that an out-of-tolerance transmission shall not exceed 6 seconds under any circumstance. If the primary transmitter develops a fault, the system should automatically transfer to the backup transmitter. If the changeover does not occur, or the backup transmitter is also faulty, the system is automatically shut down and the alarm in the tower is sounded. However, the runway at Apia was being extended and the cable was cut between most of the navigation aids and the status display in the tower. This resulted in the NOTAM stating that various navigation aids, including the ILS, were unmonitored. But unfortunately there's more. For maintenance purposes, parts of the ILS system can be shut down in a bypass mode to facilitate calibration. On that night in July 2000, the glide slope transmitter with the inoperative side lobe amplifier was left switched to the maintenance mode via a bypass switch so that the system could not transfer automatically to the standby transmitter. As a result, NZ60 only ever received the carrier wave transmission for the glide slope, and so the aircraft always sensed that it was on slope. As the carrier signal was being received, the aircraft instrument glide slope warning flags consequently were removed from view. Now let's consider what threats exist and what our strategy should be to deal with these threats. There are many possible ILS problems, but we can categorise them into 4 groups: the false glide slope, the false localizer, the erroneous glide slope, and the erroneous localizer. The false glide slope and the false localizer are byproducts of the normal ILS transmission. For example, the glide slope signal is transmitted with additional lobes above the primary 3-degree lobe. The first one has a 9-degree glide path. If this false glide slope was captured, you would have no flags, show on slope, and have a normal ident, but you would need an extreme rate of descent. The best strategy to detect a false glide slope capture is to intercept the glide slope at the initial approach fix to enable a cross-check of altitude against position. A false localizer is caused by a similar phenomena to the false glide slope, but in a lateral path. Remember, these false paths exist as a normal byproduct of correct and valid ILS transmissions. The erroneous glide slope will show that you are on slope regardless of your approach slope or where you intercepted it. You will have no flags, have an on-slope indication and a normal ident. In addition, your sink rate could look quite reasonable. Even a GPWS would not prevent an accident in this case. The alerts are inhibited if the rate of closure with the ground is within design parameters, and especially if the aircraft is configured for landing, even though the touchdown point might be several kilometres from the runway. However, aircraft fitted with a terrain awareness warning system, for example EGPWS, would receive an alert in this situation. There is one more complication. Many modern aircraft use flight management computers for lateral and vertical guidance. Once they have been programmed to intercept an ILS, they will fly to their estimated intercept point and execute a pre-programmed pitch-down manoeuvre in the order of 0.05 of a G. This will establish a rate of descent that has no bearing on the actual glide path. Once this pitch-down has been completed, the aircraft's flight control computers will react to any sensed glide slope deviation. If the glide slope signal is erroneous and indicates on slope, no corrections will be applied to the descent angle. Add this situation to the mindset of pilots that a correctly indicating ILS is valid and accurate, when combined with a distance altitude check at the glide slope capture, and you have a recipe for disaster. The single distance altitude check does not guarantee the subsequent descent path. Similarly, a single altitude check crossing the outer marker does not guarantee the glide slope is correct. The best strategy to employ is to periodically cross-check the aircraft altitude against distance during the descent. The localizer signal is formed electronically in the similar way to the glide slope signal. The erroneous localizer presents the same problem but in the lateral path as the erroneous glide slope. Again, you would have an on-centre indication, no flags and a normal ident, but the aircraft would not be following the correct path because it would not be getting any lateral deviation information. The best strategy for this fault is to cross-check the ADF or VOR pointers. They will show any tracking discrepancy if they are selected to the outer marker or a nav aid selected at the field.
The investigation also looked at human factors issues, and specifically the crucial strategies which enabled the NZ60 crew to prevent this incident from becoming an accident. These were team building, preparation, vigilance, and trust. Preparation for this flight was excellent. The crew arrived early to flight planning. They hadn't operated together before, but they reported that a good feeling of teamwork quickly developed due to the relaxed atmosphere which allowed them all to work effectively. The crew's thorough discussions regarding the unmonitored state of the VOR, ILS DME and ILS glide path, and the absence of standby power for the ILS glide path also involved the flight dispatcher. On the way to the aircraft, one of the first officers bought coffee for the flight crew and the ISD. All these team-building elements meant that this crew was functioning very well long before the event at Apia. Vigilance is what saved this flight. The pilots planned their descent and approach carefully, and the approach briefing was very thorough. During the initial stage of the approach, they confirmed the planned FMC descent profile was being flown on the DME arc by using the 1 in 60 rule. Because it was NOTAM'd unmonitored, the third pilot continuously monitored the ILS ident for any unseen eventualities. They also pre-briefed for the alternative VOR DME approach. The crew were watching and waiting, but when the clues arrived, they needed to decide which information was correct before deciding what course of action was appropriate. Probably the best qualified to comment on this process is the head investigator into this event, Mr. Dave Stobie.
Early on in the investigation, it was obvious that this crew were cautious, diligent and well prepared for the approach. They were aware that they needed to cross-check their various pieces of information, but they had a normal mindset for pilots conducting an ILS. Pilots tend to trust the most precise information. For example, they trust a VOR more than an NDB. They also trust an ILS more than any other approach aid because it allows high precision approaches. So when things didn't feel quite right during the approach, they naturally accepted the most precise information they had, which was the ILS, especially in the absence of any warning flags.
That mindset was difficult to break. The combination of a high workload managing the aircraft energy and the trust in the ILS system that they had all been conditioned to have made it difficult for them to perceive the glide path error. When the captain looked up and didn't see the runway lights, he made the mental picture fit by assuming there was weather in front of him. When they saw a descent of just over 1,000 feet per minute, the crew again made the mental picture fit by assuming the tailwind and heavy weight were the cause of the higher rate of descent. They were presented with normal centerline and glide slope indications on all their instruments. The autopilot had accepted the localizer and glide path guidance signals. There were no immediate clues available to warn them that the information being portrayed on the instruments was, in fact, wrong. The autopilots interrogated all data and found no anomalies with the status of the ILS information and therefore went to Land 3 auto land mode. The Faliolo VOR DME was the only DME not subject to a NOTAM. With the crew using this DME, the conflict of DME distance against the aircraft altitude took some seconds to resolve. The Faliolo VOR DME is 1.5 miles down the runway from the threshold of runway 08. And this required an adjustment of 450 feet to the 300 feet per mile rule to check the distance against required altitude. In the face of a centred glide slope indication, the fact that the distance was anomalous against the actual altitude, combined with the high level of trust pilots all have for the accuracy of the ILS, would have created a potential mental question of what did I do wrong? What error did I make in my calculation? Although they didn't understand precisely what was wrong, the conflict generated for each of them from the distant altitude anomaly and the apparent closeness of the lights on the adjacent island caused them each to break their mindset of the ILS being correct and make a safe decision to go around, establish the aircraft clear of terrain and above safety height, and then examine their options.
When pilots cross-check information, they do so because they are aware of possible errors. Over the years, we have learnt about many of the technical errors which occur, and we are continually improving our understanding of human error. It's easy to accept the most compelling information, in this case the ILS. This is normal human nature. What this event has taught us, yet again, is that we must remain vigilant and always be careful to validate all the information we are presented with. When the crew of NZ60 went around, they did so because their trust in the systems and the aircraft had been violated. Trust is interesting. With the open environment that had been created and the team building that had gone on earlier in the night, the crew felt sufficiently at ease to express their doubts and call the go-around. After their go-around, not only did they have to re-establish trust in their aircraft and in their navigational aids, but they also had to break the mindset of trust in the ILS, which had been established over many years of training and line flying. We associate precision with trust, so when the crew had a valid ILS signal but the DME cues were wrong, they tended to trust the ILS at the expense of the DME. We trust our instruments, especially if there are no flags coupled with a valid ident. One way to review the elements of this event is to use Professor James Reason's model, a model that you're all familiar with. The model looks not only at those causal factors which were immediately proximate to the event, the active failures, but also further back into the past to determine the contribution of other, apparently unrelated factors, the latent conditions. Let's look at some of the factors relevant to this event using the Reason model. The first offence was breached by the NOTAM terminology because there is a misunderstanding regarding the potential risk of using unmonitored or not ATS monitored approach and landing aids. The second offence, monitoring the ILS ident, was breached because the ident was present throughout the approach. The third offence, the aircraft warning system design, was breached because the degraded ILS system still provided sufficient electronic information to withdraw all the onboard warning flags. The fourth defence was breached when the glide slope intercept check was not completed. The fifth defence, the warning available from a ground proximity warning system, was breached because the aircraft was correctly configured to land, which met all the requirements of the GPWS system. The sixth defence held. The crew's situation awareness involving the unease generated at the glide slope capture, the increased workload to configure the aircraft, the proximity of the lights on the island, and reinforced by the conflict between the aircraft altitude and DME distance, caused them to execute a go-around and protect the safety of the aircraft. Although the transmission of erroneous ILS information at Apia was caused by an unusual set of circumstances, technicians are routinely required to transmit similar signals during test and maintenance of airfield navigation aids. A similar situation to that faced by the crew of NZ60 could occur to all aircraft types and to any crew during what seems to be a routine instrument approach.